Hello children, let's start with the sixth question. Give examples of two functions f n to z and g z to z such that GOF is injective but g is not injective. Not injective means, and injective means what? We have to prove that it is 1 1. So first we have to prove that f is 1 1. Then we can prove that it is GOF is 1 1 and where g is not 1 1. So f is defined from n to z, is it? So n if we take 1 2 3 4 5, and z we can take a number minus 1 minus 2 minus 3 minus 4 0 1 2 3. Now first we have to prove a function f is 1 1. So let's say fx is equal to x. So if you put n 1, so for 1 you will get 1, for 2 you will get 2, for 3 you will get 3, for 4 you will get 4, and 5 also, for 5 you will get 5. So fx, if you put fx is equal to x, it proves that f is 1 1, is it? Now we have to prove g, which is defined from z to z, is not 1 1, is it? How will we include? Now let's see. A function is defined from z to z. So let's take z. Z is what? Minus 1, minus 2, minus 3, minus 4, 0, 1, 2, 3, 4. Is it? Now if you take fx is equal to mod of x, or we can take it as x square, then if you put x, say minus x, the result will be again 1. If you do minus 2, again give you 2, and 3 minus 3 also give you 3. Similarly, minus 4 will also give you 4, and 1 again will give you 1, 2 will give you 2, 3 will give you 3, and 4 will give you 4. It means that if a function is fx is equal to mod x or x square, g is not 1 1. G is not 1 1. Is it? Isn't it? You got this? Now let's see how we will write it. How we will write it as 1 1. F of x1 is equal to f of x1 is equal to f of x2 implies x1 is equal to x2, then f is 1 1. So let us define function f as f of x as we have chosen here, is it? Where x belongs to n. So let f of x1 is equal to f of x2. What is f of x1? x1. So f of x2, x2. So f is 1 1 function, is it? Now let us define g as g of x is equal to mod of x for x belongs to z. Let's see. F x1 is equal to f x2, where x1 x2 belongs to z. What is f of? We have taken as f of x as a mod of x or x square you can take. So if you take as f of x as a mod of x, so it will become mod of x is equal to mod of x1 is equal to mod of x2. Implies x1 will be equal to plus minus x2. So it shows that x1 will not be equal to x2. So g is not 1 1 function, is it? Similarly we can take at x square also. If let f of x1 is equal to f of x2, where x1 x2 belongs to z. So x1 square will be equal to x2 square. Since x1, x2 belongs to z, so x1 will be equal to plus minus x2. So x1 is not equal to x2, where in the case where x1, x2 belongs to z. So therefore g is not an onto function. Now what remains is to prove is that GOF is 1, 1. So let's take GOF is defined from, what do you put here, f. So where the f function is defined from, f function is defined from, say, fn to z. So what you put in this GOF of x, you put value of x, f from the f, and therefore it is defined from n. What is the domain of fn? So it will define from n. And after that, what you are getting, g. What is the codomain of g? Z. So GOF is defined from n to z. So GOF of x1 is equal to GOF of x2, where x1, x2 belongs to n. So GOF of f of x1 is equal to GOF f of x2. But f is 1, 1. Therefore f of x1 is equal to f of x2. Therefore we can write as f of x1 as x1 and f of x2 as x2, since f is 1, 1. So g of x1 is equal to g of x2. If you take it as square, then what is a function of g? X square or mod? Isn't it? So x1 square is equal to x2 square, or mod of x1 is equal to mod of x2. Here x1 will be equal to x2. Why I said x1 is equal to x2? Since x1, x2, here x1, x2 belongs to n, so there is no question of minus. So therefore there is x1 is equal to x2, not plus minus x2, but x1 is equal to x2, since x1, x2 belongs to n. So GOF is injective, isn't it? Okay. Now let's move to the 7th question. This question is very interesting. Give example of two functions fn to n and gn to n such that GOF is onto, but f is not onto, isn't it? So first you have to analyze that whenever we are proving that GOF is onto function, it also shows that whenever GOF is onto, g is onto and f is not onto, whether it is written or not. In some questions they can ask directly prove that GOF is onto. When we say GOF is onto, it implies that g is onto but f is not onto function, is it? Now where is f is defined from? The f is defined from n to n. So let's take here one set like this, isn't it? N. So n is 1, 2, 3, 4, 5. Is it? GOF is, we have to prove that it is not onto function. Is it? We are not proving 1, 1. We are proving onto function. When we are proving onto function, here there should be some images. From codomain, there should be some images in the domain, then there is an onto function. Is it? So first we have to prove that f is not onto function. Okay, isn't it? F is not onto function means any one element have to prove that there is no images in codomain. So let's take f of x is equal to x plus 1. If you take f of x is equal to x plus 1, put 1. For 1 what will get? 2. For 2 what will get? 3. For 3 what will get? 4. For 4 what will get? 5. For 5 what will get? 6. Is it? We are talking about onto function. For onto function, codomain. all the element in codomain should be exhaust. Here what we find is that the element in codomain 1 does not have any images in domain. Is it? So F is not onto function. F is not onto function. So how we'll write it? For n belongs to codomain, for 1, for what we'll write? 1 belongs to n in codomain, got it? That does not exist any image in domain, such that, is it, there does not exist any element in codomain, therefore F is not onto function. See here, consider the element 1 in codomain. Okay, element 1 in codomain, 1 belongs to n, but there does not have any images of the element in codomain, therefore F is not onto function. Is it? So first point is proved. What I said, when we are proving Goff onto function, we must show that F is not onto, but Goff G is onto. Then Goff will be onto. Is it? So now let's move on to the G. Okay, what is G? G is defined from n to n. Now, what we have taken element here? Here only we will take. Okay, it's again n. We'll take this element 1, 2, 3, 4, 5. Now, when I have to prove that G is onto function, there should be some images here of 1, where now 1 is excluded here. So this anyhow have to include it in my function. Is it? Then it will become onto function. Suppose this is G. For all the element here, there should be some element here, images here. Then it is onto function. So let's define G as in 2 parts. Let us include this. How we can include? Gx is equal to 1 when x is equal to 1, and gx is equal to x. Okay, x minus 1 when x is greater than 1. Is it? Let's take this. Okay, then what will happen? Substitute here 1. For 1, what you will get? 1, because when x is equal to 1, the value of in codomain is 1. So 1 is equal to 1. What is the value of 2? For greater than, this function will be used. Greater than 1, this function will be used. So put 2 minus 1, 1. Then for 3 it will be 2. For 4 it will be 3. For 5 it will be 4. For 6 it will be 5. Now let's take in onto function. As I said earlier, for onto function, all the element in codomain should be exhaust. What I mean to say exhaust? Exhaust means there should not be any element left in codomain such that there will be no images in domain. So for 1 we have images. 1 is for 1, 1 is also 2. There should be some element. I not said 1. There should be some images in domain. So 1 has 2, 2 also has 3, 3 also has 4, 4 also has 5, 5 also has 6. So all the element in the codomain is exhaust, and therefore G is onto function. Is it? So G is onto function. Let's see here. So let us define G n to n such that G of x here, G of x is equal to 1 where x is equal to 1, and x minus 1 where x is greater than 1. Is it? So for every element Z belongs to N in codomain, there exists some element Y in codomain, therefore G is an onto function. Therefore G is an onto function. This comes from the definition of an onto function. Is it? Now let's see where the GOF is defined from. The GOF is defined from N to N. Is it? How? What? From where the N, where the F comes? What is the domain of F? The domain of F is N. And what we are getting? What is a codomain of G? The codomain of G is also N. So therefore, the GOF is defined from N to N. Is it? And GOF of X is equal to G of Fx. What is f of x? We have taken f of x as here x plus 1. Okay, we have taken f of x as a x plus 1. Is it? So in place of f of x, what we write? X plus 1. Now x plus 1. Now we have to have two choice. There are two definitions of G. As I said, there are two definitions of G. So for onto function, we must also have two definition for the onto function. One, right? GOF of x is equal to 1 when x is equal to 1, and GOF of x is equal to x for every x greater than 1. How we got it? This, see, put here. What we have here? X minus 1. Is it? G of x is equal to x minus 1. Put here x plus 1. So x plus 1. In place of this, you write x plus 1, then minus 1. So this cancel out. It gives you x. It gives you x. So that we say GOF of x is equal to 1 when x is equal to 1, and GOF of x is equal to x when x is greater than 1. Is it? So there will be, as I said, there will be two definition of onto function here. For n belongs to 1 belongs to n in codomain, there exist 1 belongs to n in domain such that GOF of x is equal to 1. And for x belongs to n and x greater than 1 in codomain, there exist x in n in codomain such that GOF of x is equal to x where x belongs to n, and therefore GOF is an onto function. Is it? Okay. On to next question. Given a non-empty set x, consider Px, which is a set of all subset of x. Define the relation R in Px as follows. For the subset A and B in Px, AR in ARB. ARB means AR in B. If and only if, very obvious, A is a subset of B. Is R is an equivalent relation on Px or not? What do you mean by equivalent? Yes, Ritu, you must be knowing. Yes, R we have to prove it reflective. Pacha? R we have to prove as symmetric, and R we have to prove as transitive. Yes. So let's see how you prove R is equal to. How you prove R is equal to reflective. AR in A. Let's AR in A implies A belongs to R. What function we have? A is a subset of B. So we are talking about A and A. AR in A implies A is a subset of A. And we know that every set is a subset of itself. Therefore R is reflexive. Is it? Okay. Next we have to prove it is symmetric. How we have to prove symmetric? AR in B. Okay. What is AR in B implies? AB belongs to R. Implies A is a subset of B. But A is a subset of B does not imply B is a subset of A, and therefore R is not symmetric. Let's take an example. Is it? Say take A is equal to 1, 2, 3 and take B is equal to 3, say 1, 2, 3, 4, 5. So what is it? All element of A 1, 2, 3 are present in B. Is it? Are present in B. Therefore A is a subset of B. But are all element of B are present in A? No. Here 4 and 5 is not present in B, so we cannot say B is a subset of A, and therefore it is not symmetry. Is it? Now, third point we have to prove is that refractive. Refractive, how will it be? A are in B and B are in C, which is belongs to R. If we prove that, then it will be transitive. What is A R in B? A R in B means A is a subset of B, and B R in C means B is a subset of C. Look here, A is a subset of B and B is a subset of C. So what it implies is A is also subset of C. Is it? So it is proved that R is transitive. So see here, let A R B and B R C belongs to R. AB belongs to R and BC also belongs to R. What it means? ARB means A is a subset of B. What it means? BRC means B is a subset of C. Is it? So it symbolizes that A is a subset of C. If A is a subset of C, means A, C belongs to R. Therefore, A R in C belongs to R. Therefore, R is transitive. And so what we proved is that R is not an equivalent relation. Why it is not equivalent? Since it was not symmetry. So it is not an equivalence. Is it? Okay. Let's move on to the next question. It's a little bit tough. So let's see that. To understand it is tough, but writing it is easy. Given a non-empty set, consider a binary operation P power set of x cross power set of x, P of x cross P of x to P of x given by A star B. Star is operation. What is operation? Intersection. So A star B is equal to A intersection B for every AB in Px is the power set of x, so that x is an identity element for this binary operation, and second, x is only invertible element in Px with respect to the binary operation x. Is it? Two things you have to understand this question here. What is a power set P set? It is a set of all subset. Is it? Of x. So if we say x include all the power set. All the power set. And from where A and B comes? A and B come from the power set P of x. Is it? So from A and B, which is a bigger set? A is the bigger. A is a bigger set. Is it? Why I am telling this? Because when we'll take an intersection, binary operation, our binary operation is A star B is A intersection B. Our operation is intersection. So this concept will be very useful in solving this sum. Is it? For an identity element. So can you say what is the definition of an identity element? Yes. Given a binary operation A star A An element E belongs to A if exit is called an identity for the operation star if A star E is equal to A is equal to E star A for A belongs to A. Is it? But what is here? What is in given set? Here in place of A, we give as, it is given as Px. So Px cross Px is equal to Px, and what we have to prove? X as an identity element. So what will be here? X belongs to P of X. If it is exit, is called identity element for the operation star if, what is here? Our A. Let us take A. We have a capital A. Capital A cross, what is the identity element we have to prove? X. So A star X is equal to capital A is equal to X star A for every capital A belongs to A. This is the definition. This is the basic definition. From there we have to define our definition. Whatever the definition says that for a given binary operation Px cross Px to Px, an element X belongs to P of A, P of X. If it is exit is called an identity operation. If, what will come here? P of, it is A, capital A, star X. Is it? X is equal to X is equal to X star A. So it should be A, capital A. What is C here? For an identity element, X belongs to P of X. If it is exit, call identity for the operation star if A star X is equal to A is equal to X cross A for every A belongs to PA. Is it? Pachakaga? You know the definition of identities? Learner? Let's see. So A star X, what is the operation? What is the operation? Intersection. So A intersection X is equal to A. Now why I written A not X? See, as I said, what is X? It is a power set of X is the power set. Is it? From X only the power set made, and where is A? A is from per power set. So from these two, which is the biggest? X is the biggest and A is the smallest, and when we take an intersection it always comes the smaller. For let's take the example. Say A is equal to 1, 2, 3 and B is equal to 1, 2, 3, 4. Okay, you find A intersection B. What is A intersection B? 1, 2, 3, which is equal to A. But A from these two sets, A is the smaller. So when we take an intersection, it is smaller set comes. Is it here? So A star X is equal to A intersection X is equal to A for all A belongs to P of X. And what is X cross A? X cross A is equal to X intersection A is equal to A for all A belongs to P of X. It means that A star X is equal to A and X star A is equal to X star A for all A belongs to PA. Thus X is an identity element for the binary operation star. Is it? This proves the first part. Now we have to prove the second part. X is only inventable element in Px with respect to the binary operation star. So what you have to do? We have to go for the second definition. Is it? Okay, Kushant, you knowing second definition? Is it inverse function? Yes. Okay, given a binary operation A star A with identity element E in A, an element A in A is said to be inventable with respect to the binary operation star if there exists an element B in A such that A star B is equal to E is equal to B star A, then B is called the inverse of A. Is it, Ritu? You must be knowing it. Is it? Now let's see how we convert it in our ratio. Is it? According to the sum. We'll start from here. An element. Is it? We'll start from here. So see here. An element X in P. An element A belongs to Px is said to be inventable if with respect to the binary operation star, if there exists B belongs to Px such that A star B is equal to X is equal to B star A for every X A, for every AB belongs to Px. So what do we prove? We have to prove this. So let's write A star B is equal to X is equal to B star A. What is our star function? Intersection. So which implies A intersection B is equal to X is equal to B star A is equal to B intersection A. Is it? Why I have written A intersection B is equal to X? Yes. What is a common in between? Got it? Intersection X. Is it? It is X is an what we proved. We proved X as an identity element, and it is an identity element. Is it? So it is A star B is equal to X is equal to B star A. In this case, it's only possible. When this will be possible, A intersection B will be equal to the same thing, and B intersection B will be also equal to the same thing. This can only be possible when A and B are equal. Got it? A and B are equal to what? A and B will be equal to X. So this can only be possible if A is equal to B is equal to B, and A is equal to B, and both A and B equal to X. What it implies is A is equal to X and B is equal to X. Let's take one example. Let's take A is equal to 1, 2, 3. Okay. And B also you take, just for example, you take 3, 4. Okay. And A intersection B is, we say X. X you take as 1, 2, 3. Is it? If I say A intersection B is equal to B intersection A, it implies the number of elements in both should be same. So this is not possible. This can be only possible if A intersection B, if I take A intersection B, what I get? 1, 2, 3. Intersection 1, 2, 3. Got it? What is common? 1, 2, 3. Is it? And if I take B intersection A, what I get? 1, 2, 3. Intersection 1, 2, 3. So it should be same as 1, 2, 3. This can be only be possible when A and B are equal. They will be having a same, equal to the identity element X. This can be only be possible when A, B and X are equal. Is it? So what we prove that X is the only element. Is it? What it implies is here, A intersection B is equal to X is equal to B intersection A. This can only be possible if A and B are equal. Then only they will have a common element which is X. So what it shows, whether it is A intersection B, whether it is element A, whether it is element B, all belongs to A, X, and therefore X is only inventable element in Px with respect to the given binary operation. Hence proof. Is it clear? Because all three are equal. If you talk about the A, we talk about the X. If we talk about the B, we also talk about the same as X. So it shows that X is only the inventable element in Px with respect to the binary operation star. Is it? Okay. Thank you very much.